So, we will look into the heat exchanger theory as a way to model heat sinks, and that can be universally applicable to many varieties of heat sink, not just parallel plate or longitudinal fin heat sinks, but also for foam heat sinks and so on. We will look at those examples in the upcoming modules, but for now we will just look at this heat exchanger theory. What we know is that heat exchanger theory was developed for fluids flowing between if it is a counter flow heat exchanger, then we have fluid entering, hot fluid entering from one side and cold fluid from entering the other side, and there is a transfer of heat from the hot to cold and it exits. So, in a heat sink, however, there is no two fluids, there is only one fluid. In this case, we will just see that the cold fluid is the only fluid that exists, and hot fluid does not exist in a heat sink. But one main thing is that the heat exchanger emphasizes on the capacitance of the flow rates, that is m dot Cp is the critical parameter that determines how much, or the capacitance ratio is the one that determines what is the maximum heat transfer rate one can achieve, which will be based on the minimum capacitance of the system. In this case, where we have a solid exchanging heat, one can understand the system to be of this nature, that the temperature profile in a heat sink typically, because the heat sink is made of copper or aluminum, very highly conducting material. Typically the materials used for heat sinks are aluminum, copper, and so when it is dissipating heat, the solid side thermal conductivity is so high compared to the fluid side, which is air typically, is that now you have a situation where the solid side can be treated as if it is it has a temperature profile. This is temperature and this is x, and that is shown as air enters from the left hand side and exits. If this is your heat sink, air enters from the left hand side and exits here. You know that the base of the heat sink shown here, the temperature is going to be fairly uniform. The temperature of the heat sink is going to be fairly uniform. However, the temperature of the air that is incoming, it is going to start at a lower temperature, that is the ambient temperature, and keep rising in temperature. Eventually, it may reach the temperature of the metal, and this is your fluid. This fluid may attain the temperature of the solid fin if sufficient length was provided to it. But so what this is saying is that now my solid temperature can be treated as if it has a capacitance that is much larger compared to the fluid side. So that gives us an idea of using the heat exchanger theory with one side of the fluid being having a larger capacitance, like a phase change in a typical heat exchanger theory, and the colder side can be treated like a typical heat exchanger. So that is what a typical effectiveness of a heat exchanger is given by the relation Q actual divided by Q max. Q max is determined by the capacitance, minimum capacitance of the two fluids in a two fluid case. So the hot side heat exchanger is m dot Cp of the hot side. This is the capacitance of the hot side fluid, and hot inlet minus hot outlet, inlet and outlet, and the cold side is the actual. In this case, we will deal that is cold inlet, a cold outlet and cold inlet, and this is your Q hot actual and Q cold actual should be equal. So defining C minimum based on the idea that I just discussed, that the solid side heat transfer temperature is going to be more or less flat relative to the fluid temperature. There will be some gradients, but it is going to be much smaller in comparison to the gradient on the fluid, which is, for example, air side. So one can write the expression of effectiveness in terms of either on the hot side or the cold side as mCp of the hot side into T hot minus T hot out. This is your Q actual divided by C minimum T hot in minus T cold in. Similarly, we can write the expression for effectiveness based on the cold side as well. However, assuming that cold fluid has the C minimum, in this case as I explained in the previous plot, the hot side or the solid part is going to be fairly constant in temperature compared to the temperature. Let us say the temperature rise of air side is 40 degrees, while the temperature of the hot side is going to be 2 degrees Celsius. So, comparing the 2 degrees versus 40 degrees, we see that one can think of the solid metal as something that carries lot more capacitance compared to the fluid side. So, using that idea, now we can write effectiveness in terms of C min, and using cold, essentially C min is same as the MCP of the cold fluid and with that we get cold out minus cold in divided by T hot in minus T. This is your, so what it gives us is an expression in terms of Q actual is nothing but epsilon times C min or MCP of the fluid, cold fluid, times T hot, which is the maximum temperature of the surface, minus T cold in. Because we are already assuming that the maximum temperature of the hot side is considered to have T hot in is equal to T hot out. So, with that we can say that my base temperature is some kind of maximum temperature that is equal to T hot, and now I can rewrite this expression as my heat sink part as Q actual epsilon into MCP of air if air was the fluid, T base which is the hot side, minus T air in. So, this is essentially the heat exchanger theory modified to account for the for a heat sink purpose. Now, how do I define the effectiveness is the next question. We know that NTU or number of transfer units relationships are well established in heat exchanger theory. We can make use of it, and we can define NTU as UA by C minimum, and as we move forward. So, NTU is nothing but number of transfer units is nothing but heat transfer coefficient into A effective. This is the surface area or effective surface area that is utilized divided by the C min, which is the MCP of the airs. So, we can get this expression. This, as you can see, is the expression for NTU, and if we plug this into the effectiveness equation, you get 1 minus exponential of minus NTU. This is the expression that one gets for one fluid case. This is well documented in the literature in textbooks. So, effectiveness is equal to 1 minus of exponential of minus NTU, and substituting for NTU this HA effective divided by MCP. So, now I can define my heat sink as the resistance of my heat sink as delta T by Q. This delta T is nothing but T base, which we called as T hot in, minus T cold in by the heat transfer rate. This T cold in is same as before. This T cold in, we'll call it, sorry, we'll call this T air in, and this T air in was T cold in the previous discussion. So, this is nothing but 1 divided by m dot Cp times effectiveness, and if I substitute m dot Cp and 1 minus exponential one dot 1 divided by m dot Cp into 1 minus exponential of minus HA effective divided by m dot Cp. So, this is the resistance of the heat sink. So now if I know my flow rate, I can calculate the heat transfer coefficient. I can also obtain my surface area efficiency, surface efficiency. You have mass flow rate known to you, specific heat is considered to be constant, and with this expression now I can calculate the resistance of the heat sink. And we discussed that in the previously, that just having this as the model of efficiency is not a good approach, and we can see that if I use that 1 by HA and calculate the efficiency, and this is NTU, which is this factor that is changed here. NTU is fixed to 0.01, the efficiency is only 1%. In this case, the heat exchanger theory, which is this model, and this is the so called R thermal, the heat sink model is called R thermal, and this we call heat exchanger HTX in this discussion, or HTX is what is shown here. And if we calculate the ratios, we see that when the NTU is small, that means when the fin's density is not high enough, then both the models are predicting very closely. As you increase to higher and higher fin densities, the error encountered by the R thermal model is so large compared to the heat exchanger theory, and you can even get 400% wrong as we go away, because at higher densities the this model cannot capture the impact of the mass flow rate, while here the heat exchanger theory nicely captures it in the form of NTU. So that's why we will use this heat exchanger theory in the upcoming discussions, and the same idea of 1 divided by m dot Cp can also be used for cold plates or liquid cooled cold plates and so on. So moving forward, so in a typical air cooled design, you have fans employed, centrifugal fans or axial fans, or even some kind of special designs. Axial fans are used in servers, centrifugal fans are used in laptops, where air is pulled from one side, from the center in this case, and pushed radially out, and this is where a heat sink is typically mounted, and close to the vent, and a heat sink is mounted and air flows across these heat sinks. So the fans on the other hand can be suction or versus positive, and most of the laptops have a suction side where they pull air from outside through a screen or vent, and then they push it across the heat sink. So fan laws are important because we need to acknowledge that when we are designing heat sinks, we need to know what is the fan behavior, fan system. So in a typically if I draw for a heat sink pressure drop versus flow rate, the pressure drop versus flow rate will look like this. The pressure drop increases as my flow rate increases. However, a certain fan, this is a fan curve typically called, only generates a certain flow rate. This is for a fixed RPM of a fan, and RPM of a fan is fixed, and the size of a fan is fixed here, and so you get a curve like this, which is the pressure drop. When the fan produces zero flow rates, you get it can withstand highest static pressure. When the pressure drop across a pressure drop that it has to overcome is zero, then the flow rate is maximum, and there is a region of uncertainty which is typically avoided in fan flows. This is the region of the so called stall region, where you see that if I were to draw a line, that there can be two pressure drops. For the pressure drop is constant, but the flow rates can be different. So you run into a situation where the fan can oscillate between points and can create noise and other issues. So we try to avoid, and we operate the fan. So now superimposing this in here, this is the device or the heat sink curve, and where it crosses over meets, this is called the operating point of a heat sink. And depending on whether the fan is able to deliver a certain mass flow rate or not, then one has to either increase the RPM or change its size. If one were to change its size, then one can use the fan laws that are known for the same rotor diameter. If I were to increase the RPM, what will happen is that as I increase, if the fan is same, if I increase the RPM 2 divided by RPM 1 is going to be, my flow rate is going to be just a linear function of RPM. However, the pressure will increase as a function of square of it. The power consumed by the fan will increase by cube of it. So you can use the fan laws to assess whether the given fan is going to work for you or not by using the fan laws and the pressure drop and heat transfer, and that completes the fan heat sink model combination with the help of heat exchanger theory. And also one can account for gas density and so on, and that can change the scenarios. So moving on, now what we found so far is that we can use heat exchanger theory as a way to model these, and many people have used the heat exchanger theory to show that the prediction from the heat exchanger theory is quite close to the experimental values ducted heat sink configuration. So, but it does not provide necessarily a physical understanding of the system. So, one of the nice approaches that was developed is that longitudinal fin heat sink, how do I optimize the fins? That is just prediction previously. Now, how do I optimize, or what is the best way to put my fins such that we can have an initial guess that is much better than just randomly choosing some dimensions and going about some fin thickness and so on. So, one of the, if I had a fixed mass flow rate as a constraint, will there be an optima? If I have a fixed pressure drop, will there be an optima? Or optima means increase or maximization of heat dissipation, or if there is a fixed pumping power, prescribed fan curve. So, all these different scenarios one can, as we discuss in the heat transfer enhancement, you can use the same principle over here and understand the optimization approaches, but we are going to look at some discussion on natural convection cooling versus forced convection cooling. First we will look into natural convection cooling and discuss how to place the fins, how to place them apart or keep them closer so that the maximum heat transfer is maximized. So, we will make use of some of the, and this natural convection heat sink is quite commonly used in telecom sectors, and natural convection is often used. You can see the phones dissipate heat, smartphones dissipate heat by natural convection and radiation. Whenever we talk about natural convection, we have to account for radiation, and in most of the cases the contribution of natural convection and radiation are equal, meaning that if the heat transfer rate is 2 watts, and half a watt will come from natural convection and half a watt will come from radiation alone. So, in such situations, now natural convection, whenever we talk about natural convection, we have to account for radiation effects. So, let us look at a typical PCB configuration. If there is a telecom type cabinet where we put a base station on a tower, where fan failures is a very challenging situation. If fan fails in the top of a tower, someone has to climb all the way to the top. So, typical telecom sectors may not prefer fans if it is not needed. So, here is an example where a natural convection cooling is employed, where there is a, these are PCBs, or it can be fins, for example, mounted on a back plane. This is if it is a PCB. It can be a fin or a natural convection heat sink. So, what kind of boundary conditions can we use? Isothermal, isoflux, symmetry, and so on and so forth. So, here we are going to treat them as isothermal because that is the maximum temperature that one has to account for. We do not want the board to go beyond a certain maximum temperature. So, we are going to say that the boards are to be maintained isothermally, and we are going to find what is the spacing that we need between the boards, what is this spacing, so that a heat transfer is maximized or dissipated from these boards. And we have to understand two limits in this case. If I were to put one isothermal wall and the other isothermal wall separated by a distance d, initially as flow enters there is a boundary layer growth that happens closer to the wall, and as if the channel length is long enough, even the natural convection case will see fully developed flow at the exit of the duct. So, in the fully developed flow limit, where the boundary layers merge from the both sides of the wall and form a fully developed flow, we can write a heat transfer coefficients, that is where the two boundary layers are interacting. You can see at the lower end the boundary layers are not at all interacting because this is a flat line. The core of the flow is constant, only a boundary layer is seen up to some certain distance here. As it flows across, it merges. So, if the boundary layers are interacting, then we can write nicely an expression for heat transfer as Q equal to HA into T wall minus T fluid, where T fluid is nothing but your fully developed flow. You sort of assume a certain mean temperature to it. This is the fully developed flow limit. On the other hand, if it is an isolated plate limit, that means this boundary layer does not see or interact with the other side plates boundary layer, then one can think of it as if it is an isolated plate, that is a vertical plate where some boundary layer is developing. So, this sets us two limits on the heat sink or performance, and that is what we will make use of, and this was done by Bejan in convection heat transfer books, assuming that the walls are at some isothermal temperature and the spacing d is to be manipulated. So, we look at the limits when the spacing between the plates are very large, then we encounter the isolated plate limit. If the plates are placed very closely like this, then we encounter the next limit, which is the fully developed flow limit. So, if there are n number of boards with this L is the total length and D is the spacing, then if we ignore the thickness of the board and we ignore the thickness effect, then we can calculate the number of boards to be L by D. And we want to see how to space them, and that is the goal. And if we go recognizing the two limits, which is d equal to tending to 0 and d tending to infinity, that is d tending to infinity means it is so spaced apart that the boundary layers are not as was shown previously. It is so spaced apart, the boundary layer from one wall and the other wall does not see each other or interact thermally. Interaction here means thermal interaction. So, on the other limit where the plates are placed close, then you will see the fully developed flow. When they are placed close to each other, if they are placed close to each other, the fully developed flow will start right from the beginning. So, that is the second limit, that is the d tending to 0 limit. So, with these it can be shown for d tending to 0 limit, which is the fully developed flow, we can get the expression as this. This is just purely based on m dot Cp into delta T. Q is nothing but m dot Cp into delta T. Here mass flow rate is accounted in the form of rho beta delta this delta T, T naught is T wall, and so you can use this expression to get m dot Cp, and that divided by 12 times the nu here is the kinematic viscosity. So, for the total number of assemblies, Q total is L by D is the number of plates into this expression, gives you the total heat transfer if the plates were kept so close to each other. And you can notice that D and D cube get cancelled and you get D square, and Q total is proportional to D square. Okay. So, the other extreme is that we have D tending to infinity. It means isolated plate limit, the boundary layers are not interacting. In this case, the heat transfer coefficient is given by a simple vertical plate and there are two sides to it. So, having 2 and times the n number of blades to it, because there is a boundary layer developing on this side and on that side. So, that is what 2 is giving you, and you have heat transfer into area into delta T, and heat transfer coefficient is given by this correlation. So, this gives us, if you look at the expression for Q, it is inversely proportional to T. So, you have one case in the D tending to infinity case is Q is inversely proportional to T, and D tending to 0 limit you have D square. So, they are opposing trends. So, if I were to plot this, this is your d square trend and this is your, the crossover point is where the optimum spacing is, and this is what is given in Bejan's convection heat transfer textbook. And you can see that this can be shown to be true after some experiments and numerical simulation, and it gives us an optimum spacing using these points, that is setting the d tending to 0 limit and the infinity limit equal to, and we can arrive at a d optimum at that point, and it turns out to be a function of Rayleigh number and this factor 2.3, and using this d optimum into any of these expression will fetch you the q maximum that can be obtained as well. So, this gives us an idea of how to obtain maximum heat transfer or optimize the spacing between PCBs or heat sinks fins to achieve maximum heat transfer. And with this we looked at the natural convection cooling aspect of how to design or space the heat sink fins. Now we will look into, the next will be to looking into the spacing between the fins for a forced convection situation. We make use of the same method of matched asymptotes. This is one asymptotic limit, this is the other asymptotic limit, and so this is called method of matched asymptotes to obtain the optimum spacing required for the forced convection part. So, that we will look into the future module.